Okay, the first thing we're going to look at is just some of the general theory behind IR spectroscopy. And here we have a sample spectrum. This is an IR spectrum of ethanol. And you can see along the spectrum we have all of these different peaks going across it. So we want to find out what about this molecule causes these peaks to show up at different regions of the spectrum. So the first thing we want to think about is really the nature of the covalent bonds and the fact that a covalent bond is not static. So if we just do a simple example, we'll use HCl, where the hydrogen and chlorine are bonded by a covalent bond. And we can use the analogy that this bond is kind of like a spring. So the hydrogen atom is connected to the chlorine atom by the spring. And now the spring, we can stretch the spring by adding energy. And for IR spectroscopy, the energy is light. So when energy is put into this, the spring will be stretched. So what's happened here is energy was absorbed. Now, that absorption of energy is what causes a signal to show up on an IR spectrum. So a couple things to consider. First, nearly all compounds that have covalent bonds are going to absorb energy at certain frequencies of the electromagnetic spectrum. And they're going to absorb frequencies in the infrared region. And this IR absorption is quantized. So that means only select energies are absorbed by a particular molecule. And since different molecules are going to absorb different sets of energies, different molecules then have different IR spectra. So if we compare ethanol and diethyl ether, okay, both compounds have covalent bonds. They have carbon, oxygen, and hydrogen, but you can see they have very different IR spectra. And the reason is because the different nature of these molecules, they have different bonds, they absorb light at different energies to give very different IR spectra. Now we can relate energy using this equation E equals h nu, which equals hc over lambda. And of course, E is energy, nu is the frequency, and lambda is the wavelength. And if we sort of compare this to an IR spectrum, down here at the left end, is high energy, and by this equation we can say as energy increases, the wavelength decreases. And then of course on the right end of the spectrum, there's a low energy but a high wavelength. Now when a molecule absorbs IR energy, it's causing an excitation in their vibrational motions. And on the spectrum, we can see that the units are actually reported in wave numbers. which is inverse centimeters. And we have an equation for this. So the wave number is just 1 divided by the wavelength. So a higher wave number corresponds to a lower wavelength. So here where we have high energy, we also have a high wave number. So at the left we have 4,000 wave numbers. Down at the right we're clear down to 400 wave numbers. And again, the units of wave numbers is inverse centimeters. Now a molecule has different normal modes of vibration, and these include stretching and bending. So here we can just see for sort of a CH2 moiety in a molecule, there's actually 6 different modes of vibration. The CH2 can stretch, so we can have a symmetric stretch or an asymmetric stretch, but also the CH2 can bend. So this bond angle can sort of decrease and increase in a bending, and you can have both symmetric and asymmetric bending. And we're going to look at sort of an animation of some of these in just a minute with water. But each of these different stretching or bending vibrations, they occur at a very discrete energy level. And when the frequency of the IR light that's coming through that molecule matches the frequency of one of these stretching or bending modes, IR light gets absorbed, and that's going to produce a signal on the spectrum. So just this CH2 in the molecule should actually have 6 different signals in an IR spectrum. For example, here we're going to take a look at a water molecule, and below it is just a sample IR spectrum of water. And water has these different places where it absorbs IR energy to give these different vibrational modes. So the first one here we'll look at 3727, we can see we have this stretch between the oxygen and hydrogen, and this in fact is an asymmetric OH stretch. Then if we move on to 3607, it's another type of OH stretch, but this is a symmetric OH stretch. So another place where this molecule absorbs IR energy. And then finally down here at 1640, we have a bending. So HOH bending, and this is an in-plane bend. One last thing I want to take a look at is just the y-axis. So we've looked at the x-axis to see what the wave number actually means, but what does this %t on the y-axis mean? Well, %t is just % transmittance. Okay, and what that means is that's how much light is actually transmitted through the molecule. So we see this large signal here that only has about 10% T. That means only about 10% of the light got transmitted, but 90% got absorbed. So that's why this corresponds to a particular vibrational mode, because this is where energy was absorbed, resulting in very little energy transmitting through. If the IR radiation at a certain wavelength gets absorbed when it passes through a sample, then the intensity of the interferogram for that particular wavelength is going to decrease, which then changes the interferogram that exits the sample, and then that's detected by the detector.